Okay, good morning, good afternoon, one and all. So, today we are going to see the case study for the module number two. So, we have done so far block reduction technique, many numericals we have solved. We have done a signal flow graph, there also many numerical have been solved. So, tomorrow we'll be having a extra session from 3 to 5. Tomorrow is Saturday. So, there we will only do numerical. So mainly our target will be to solve numerical from module 1. Okay. So coming 4 lectures and tomorrow's lecture, that is the 6 hours, we will be only solving numerical. Many type of numerical we will solve. So tomorrow basically we will solve numerical from module 1. That is mechanical system, electrical system modeling. And whatever numerical is uploaded in the group, so I think madam has uploaded some 10 numerical in the group. Those numerical we will try to solve. So it is from a specific book of Ganesh Rao. Solutions are given, so we will attack all those numerical tomorrow. So mainly we will solve numerical from module 1 tomorrow, and if uh, time is there, then we will be going for numerical from module 2, that is signal flow graph and block reduction. So coming 4-5 hours, including tomorrow, it will be only different types of numerical. So before going for module 3, mechanical system modeling, electrical system modeling, block reduction, signal flow graph, stability, characteristic equation, pole placement, various types of numericals we will complete. So today's lecture is not on numerical. Today's lecture is on theory, and it is about what is the way to model a physical process. So modeling of DC motor. So that is another session I'm planning to record myself and upload for you. That is DC motor is very well used in electric vehicles, or there are many applications of DC motor. One of the main application of DC series motor. So DC motor, there are various types. So one is DC series motor, and there is DC shunt motor. So what is series, what is shunt, all those things you should know first. I'll try to explain that. And main application of DC series motor is for lifting purpose. So whenever there is a crane, there is a hoist, there is a lift. So sudden jerk is required at the starting. So it's a kind of an impulse function. Okay. Whenever this kind of applications are there, that is initially just in one pull, I have to lift something. There, DC series motor is applied because DC series motor is having very high starting torque. That is the first thing. Second is shunt. So why it is called DC shunt? Why it is called DC series? I'll try to explain. That modeling we will do. It is all given in the book of Dorf. In the second chapter. Okay, so the Dorf book is already given to you. The 13th edition of the book of Dorf and Bishop is already given to you. So today, whatever we are doing, it is also a disk drive read system. That means it is a rotatory motion kind of a system, and we have seen how to model a rotatory system. Okay, so we have seen there is inertia, there is rotating friction, there is rotating velocity, angular velocity, and also all those things we have seen. How to put all these things together to model a physical system. So what is a disk drive read system? So nowadays you might not have, or I don't know, maybe another 4 or 5 years back, these things were in use. So what is a disk drive read system is, we have all seen hard drive, that is a CD drive and all those things. Okay, so there, that is actually optical read kind of a thing. Okay. So there is a head, and on that head there is a sensor, and below to it a disk is there. So disks are having all tracks and everything. So the tracks are there, and above it the disk is there. So whenever the track passes from the head of the disk at that time, there is some interaction between the disk and the track, and accordingly signal is produced. So rotation of the track below the disk, and changes in the track, ups and downs and all those things. So signal is encoded there. So disk is actually for reading whatever is encoded. Sorry, uh, head is the disk drive read system. So the disk head is the thing that is trying to read what is written on the disk. So we will see mainly the model of the motor, and they have actually borrowed the model from another DC series motor, DC motor model, which is explained previously. So we are not doing that, but while uploading this slides, I will give you a reference of that. Okay, so mainly we are seeing an application of block reduction technique. So that is not a difficult part, that is the easy part, but main thing is to know what is a disk drive read system. So here a disk drive read system is shown below. It is shown that head mount for reader showing flexure. Okay, so here this is called as a flexure, and here this is a L kind of a thing you can find here, and through this the disk moves actually. Okay, so the disk is here in this side, so the disk moves through this, and then this thing is picked up. Okay, so whatever signal is embedded on the disk is picked up. So goal for this disk drive system, so there's a disk drive read system is there. So goal here, whatever we are doing, is to position the reader head accurately at the desired track and to move from one track to another. So there is a controller obviously, and this is the plant. Okay, so this is the process, this is the plant, and this is a sensor. Okay, so sensor is sensing, so this is a sensing process, and there is a controller. The controller is actually controlling the speed of the disk drive system, and the disk is the process. So this is first you have to know. So the goal is to position the reader head accurately at the desired track and to move from one track to another, because if you can see there are a lot of concentric circles on the disk. So the disk read has to read the data from many tracks. Okay, so each track the information is embedded. So the plant, the sensor, the controller are to be identified. So what is the plant? Who is the plant here? So whenever you are finding a closed loop system, so there first there is a error amplifier, then there is a controller, then there is a plant, or there is a process, and finally there is the output, and from there is coming a feedback, and the feedback is nothing but there is a sensor. Okay, likewise, so we have to identify all these elements here. Okay, so that is our main job. So the disk drive reader, so this is the disk drive reader, this is the head, this is the arm, this is the motor. Okay. So the disk drive reader uses a permanent magnet DC motor. So it's a PM DC motor, permanent magnet. So inside DC motor, there are actually two coils. One is called as a field coil, which produces EMF, or sorry, which produces MMF, or which produces a magnetic field. So first thing is field coil, and second one is armature coil. So what is the principle? The principle of DC motor is a current when a conductor is placed in a magnetic field, it experiences a mechanical force. That means there should be two input. First input should be electrical input to the motor, that is given to the armature. So a conductor carrying current. So how can a conductor carry current? If we are giving a external input of current to the motor, then only it can rotate. So first input to the motor is a electric supply. Somebody says motor as a electrical to mechanical transducer, or electrical to mechanical energy converter. So what we are first giving is, we are first giving an electrical signal that is given to the motor, and that is given to the armature conductor. So armature conductor carrying current. Current is supplied externally. That current, when it enters the motor, it does another thing. What is that? Fleming's left hand rule. So Fleming's left hand rule says that current carrying conductor, so current carrying conductor in the middle finger is placed in a magnetic field. So direction of magnetic field is given by the first finger. So what is the direction of magnetic field? It is south. So this is pointing in this direction means below, behind there is the north pole, and here there is the south pole. So is the direction of flux. And then there is the direction of current, top to bottom in the middle finger. That means top is positive, bottom is negative. So this is the direction of current. If these two are there, then there will be a force. There is the actual mechanical output. So two inputs, MMF, that is a flux input, second is the current input, and third there will be a mechanical force output. So this is actually motor principle. So whatever electricity is being given to the DC motor, it does two things. First, it supplies the current to the armature conductor, that is this middle finger, this is the input. Second, which is the main thing I was going to explain, it creates a electromagnet inside the motor. So that electromagnet is actually produces a magnetic field, mmf. So two things are created inside the motor after we supply electricity to the motor. First thing, there is produced a emf, or there is produced a current by whatever electricity we are giving to the motor. First input. Second input is there is a coil. Okay, so we know how to produce electromagnet. So there is a winding kind of thing, there is a ferromagnetic material. On that, if we are supplying current, so through that coil, if you are supplying current, then there is a electromagnet produced. So whenever there is electromagnet produced, flux lines are produced. So if there is a flux line, first thing, and if there is a current carrying conductor, and then there is a relative motion between them. Okay, sorry, if these two things are there, then there is produced an electric relative motion between them. So every motor there has one give actually electricity input, but from the electricity input that gives the mmf. There is a magnetic flux is produced from that electrical input as well. Motor uses a permanent magnet. Now here that field creation is not there. So in this case, I told you that for motor rotation, two things are required. First is there should be electricity through the conductor. That is happening. So we are giving current to the disk drive motor, but whatever electricity was being given to create flux or the field or the magnetic field, that thing is not here in case of permanent magnet, because permanent magnet motor uses permanent magnet. So there are two types of magnet: electromagnet and permanent magnet. Electromagnet requires electricity to produce that flux line, but permanent magnet already the flux lines are there. So in disk drive, we are not using electromagnet. In disk drive, we are using permanent magnet. So disk drive reader uses a permanent magnet DC motor to rotate the reader arm. So this is the reader arm. Okay, this thing actually rotates, and the DC motor is called as a voice coil monitor. So this is the voice coil monitor, and this is the arm. So this arm rotates, and this is actually picking up what is the signal embedded in the disk. The read head is mounted on a slider device which is connected to the arm shown. Okay, so there is a slider device here, and this is actually on the arm shown. This is a construction, so a flexure, okay, spring metal. So this is the flexure of spring metal. Okay, is used to enable the head to float above the disk at a gap of less than 100 newton meter. Sorry, 100 nm. That is the nanometer. I'm sorry, not newton meter, 100 nanometer. So what is there? So this thing, this flexure actually rotates above the disk track, and the gap is very small. That is 100 nanometer. So this whole thing is rotating, and at the back there is a motor that is making this thing rotate, and this is the arm which is sliding. So it can go end, it can go come out, and all those things. It rotates, and this is actually the sensor. This is the head, disk head, and actually this is picking up what is the signal embedded inside the disk. That is the thing. So the thin film head reads the magnetic flux and provides a signal to an amplifier. So actually this thing, this head, whenever it rotates on that disk, the difference, the gap between of 100 nanometer. So then this thing is actually picking up what is the signal actually embedded on the disk. So I told you very rough thing. Actually, this is the mechanical part of the disk drive, but exactly how the signal is picked up, we have to go through. So there are videos available in YouTube. Please check that on how exactly this sensor is picking up signal. Okay, it is not a very easy thing, and you can see that the gap is 100 nanometers. So a very perfect alignment has to be there. Okay, so just pick up. So only thing I wanted to tell you was there is a motor, there is an arm, this is a sliding arm, and there is a flexure, this is a flexible kind of a thing, and there is a head. Okay, so this is the overall system. Now the whole system you can put in a closed loop system. So this is the basic block diagram model of a disk drive read system. So what all things are there? There is a control device or amplifier. So whatever signal are there to control the disk drive, okay, that signal is actually passed through this head. So there are two signals. One is control signal, and one is the signal which is embedded in the disk. That signal is not being talked about here. Whatever signal is embedded in the disk, this is not being talked about. that signal. So what is the amplifier? Amplifier is actually amplifying if there is any that signal, if there is any misalignment in the disk position. So that control signal is being amplified by this. Okay, so this is control device amplifier. This is the error. What is the error? Desired head position. So where the head position should exactly be. What is head? As in the previous diagram, this is the head. Okay, so for every track we know when the track is being read after this position, the head should move this way. So that is actually the desired head position, and where the head is actually positioned at present. So difference between these two. So there is the output CS, and this is actually input or control signals. So on this line, sensor. This is okay. So this is the head, and this is the flexure. So this point is the main process. So controlling of this main process is to be done, and this is actually the closed loop system. So at closed loop system we find is at the initial stage there is the desired head position, that means where the head should be placed and where the actually where the head is. Okay, so depending on this two signal and their difference, it is decided that how to control the position of the head. So this is a closed loop, ideal closed loop system. There is a controller, and this controller is actually producing a signal to the process. So the process is nothing but the DC motor and the arm control. So DC motor controls the rotation, arm controls the linear sliding kind of a thing. That is, arm is coming left and right or front and back, because it has to place the head across all the tracks of the disc. That's why the arm has to slide. Now, this sensor, what is this sensor? This sensor is not actually the sensor which is picking up the signal on the disk. It is not that sensor. This sensor is actually trying to find out what is the position of the head. So this is the read head and the index track on the disk. So this is actually sensing of position of the head. So this is not actually the signal pickup. This is the position pickup of the head position. Okay, and what is the desired head position and whatever is the actual head position, their difference is nothing but the error signal. So whatever is the actual head position, that is the output, that is getting multiplied with this block, that is the sensor read and index track on disk. So this is sensor is producing, having some gain or something, internal gain or internal transfer function. That thing is getting multiplied with actual output, and they are actually given as the signal BS, and this desired head position is actually RS. So RS minus BS is the error signal that is being given to the controller. So this part is actually controlled by the microcontroller of your computer or whichever system it is part of, and that thing is producing the output depending on desired position and actual position of the head. Error signal is generated, this is amplified, and again this is given to the DC motor. Now DC motor just model we will take, okay, from a previous model. It is done in the same book of Dorf. I have shown you that at page number 122 you will find this model of disk drive system, and this is a part of your SEE preparation or IA preparation as well, because whatever case studies are given from that also questions will be asked. So this we will find in the book of Dorf. Please find out. It is not found in the book of M. Gopal. So page number is 122, Dorf edition 13. Okay, so output of the actual arm is coming at the actual head position. Now, if we want to show it by means of a parameter, then exactly how it looks like. So sensor is taken as 1. Okay, so I told you that feedback, it is taking 100%. So HS is taken as 1. This is the feedback signal. KA, KA is amplifier gain. So whatever error signal is coming, that is getting multiplied with KA. So there is no S here. So this is just a multiplying factor, 2, 5, 10, that kind of a thing. So this is called as a gain, and it's a very important factor when we will be doing root locus at that time. वो पूरा KA का खेल है. Okay, so this is called as a DC gain of the system. So this is the amplifier gain in the forward path. Now this GS and KA can be multiplied. Now what is this GS? How have we got GS? This question you cannot ask, because this GS I also cannot explain, because this is a motor model. Okay, and what are all these parameters? J, we know what is that, inertia. L is the inductor, R is the motor resistance, B is another parameter. So all this parameter I will explain in the next slide. what are all these parameters. So these are all internal motor parameters, and how this model is developed, that is actually given in the some another chapter in the same book. Okay, so if you want, I will give you the reference, you can go through. Km is also another gain for this process. So you have to understand that this is a third order process. Why this is a third order process? Because this is S, again this is JS, again this is LS. If you just multiply all this and get 5 parameter or 4 parameter at the denominator, you will be finding that one parameter JLS cube will come. Okay, so this GS, this is the forward gain, this is a third order process. And now you are finding H is equal to 1 Ka. So if you are doing it, it will be Ka into GS, that is called as the main forward gain, and this is 1. So what will be the overall transfer function? It will be Ka into GS divided by 1 plus Ka into GS. So if you are trying to find overall transfer function, it will be Ka into GS at the numerator divided by 1 plus Ka into GS into 1. Okay, so it will be the overall transfer function, that will be Ys by Rs. So here are some inputs to it. So assuming the accurate read head, that means read head is working perfectly, the sensor has a transfer function Hs equal to 1. So in the feedback path, this is actually called as a Hs equal to 1. This is actually the sensor gain, the model of the permanent magnet DC motor and a linear amplifier. So this amplifier is a linear amplifier is shown in above figure. As a good approximation, we use the model of the armature controlled DC motor. So this is actually the armature controlled DC motor model, and how this thing is developed, I will give you that page number also. You just go through. If you cannot understand, I'll help you out. Okay. So when we are in the chapter number 5, so their state variable modeling is there. There we will do what is the modeling of armature control DC motor. Okay, so this model will develop first, and then we'll develop the state variable model of that. It is not difficult. Okay, only the motor parameters we should know, from there we can find out. So as a good approximation, we use the model of armature control DC motor. The model shown in above figure assumes that the flexure is entirely rigid. So whatever flexure is there at the head, this is actually rigid and does not significantly flex. It doesn't move much. In future control designs, we should consider the model when the flexure cannot be assumed to be completely rigid. So if the flexure is rigid, then one type of response we get. If the flexure is not rigid, then also one type of response we get. Now what are the parameters? So what are the parameters we can come to know? So inertia of the arm and read head. So the inertia of arm and head, they are having a mass and they are rotating. Okay, so they are having an inertia that is given by J. So whatever is mass in linear translational system, that is actually inertia in case of rotatory system. So whatever arm and read head is there, we have seen that half m r square or something was the formula for inertia. So that is that. Friction. So whenever the head is rotating, so there is a 100 Newton meter gap, 100 nanometer gap. I'm sorry, not Newton meter. There is a 100 nanometer gap between the head and the disc, but whenever there is a rotating element, it is being opposed by air. Okay, so there is always a friction, and that friction is equal to, is given by B. And what are the typical values? It is given here. So B is 20 Newton meter second per radian. Okay, and inertia of the arm and read head, it is 1 Newton meter second square per radian. So these values and this units, please remember. Amplifier is the first amplifier. There is a error amplifier. It can have a gain of 10 to 1000, any value you can take. Armature resistance. So I told you that it is a DC motor, and the DC motor is having two coils inside it. One is called as a field coil, and another is called as a armature coil. So field coil does what? Field coil produces the electromagnet, but in this case we are using a permanent magnet motor. That means there is no field coil in this case. So there is only armature coil, and that is having resistance of R. It's a very small resistance, 1 ohm. Motor constant Km. Okay, so motor is a mechanical part, so there are a lot of other losses and these and that. So together, there is a factor in the motor that is given as Km 5 Newton meter per ampere. It is given, and this is armature inductance. So whatever coil is there, that armature coil, that is having resistance and that is having inductor as well. So L and this are there in series. So L is armature inductance, Km is the motor parameter, R is the armature inductance coil resistance, K is the amplifier. This gain we can select. So if we want very high output from the head, then we can take K almost equal to 1000. Okay, so we can play with this gain. And I told you that more is the gain, less is the system stability. So in root locus, what we do is we play with this gain and we take a system from stable to unstable or unstable to stable. So root locus plot we will be doing in module number 4. It's all game of this Ka. So whatever is the amplifier gain, what is the boundary condition that for stability. So we will find that this amplifier is actually playing a very big role in overall system stability. So if this value is very less, maybe 10 or 15 or 20, then the system is stable. Poles are all in the left hand side of S plane, and now we are able to increase the gain as per our wish. We are increasing it gradually. We find that suppose if K is equal to 150, at that time the poles are on j omega axis. And if you are making the Ka greater than 150, then all the poles are getting shifted to the right hand side. Same thing, a car we are driving 60 kilometer per hour, it is perfectly stable. The car is 100 kilometer per hour, it is on the verge of instability, so it starts shaking. So shaking means it is almost going to the unstable. And if we are driving the car at 120 kilometer per hour, obviously there will be an accident and there is an instability. So that 100 kilometer per hour, that is actually the marginal stability. 60 kilometers stable, increase the gain, give more acceleration, car is trying to get unstable, and further increase the gain, car becomes unstable. So K is a very important factor. What value of the K we should select so that we get proper signal output. So more is the K value, signal will be more and more proper. Bigger signal we are getting at the output. But too much higher value of K will disrupt the system stability. So this K is a very important thing. We will see about it later on. So what we are finding is GS. So if you see this thing, GS is equal to Km divided by S, Js plus B, Ls plus R. So Km divided by S, Js plus B, Ls plus R. L they have said this is the armature inductance, R is the armature resistance, J is the inertia of the whole system. It's a rotatory kind of a system, and B is the friction. Okay. So likewise, so this is a third order system. GS is a third order system, and the GS is a type of the GS is 1, because here, so for the first time I'm telling you what is the definition of type. So type is found from GS into HS. So GS into HS is called as an open loop transfer function. You have to multiply GS with HS. So in this case, HS equal to 1, it is taken. You can find here HS equal to 1 taken, feedback gain. So GS into H is equal to same as GS, and in GS, whatever is the power of a separate S. Okay, don't see this S plus 20, don't see this S plus 1000. Just see how many S are there separate. So first you have to see GS, multiply that by HS. So GS HS in this case same as GS. In that you have to see how many separate S is there. Not S plus 20, not S plus 1000. So this is only S. Okay, that means S plus 0. How many S are there? So if it is S raised to 1, that means this is a type 1 system. If this is S raised to 3, that means this will be called as a type 3 system. So how to find the type of a system? The definition is GS into HS, forward gain into feedback gain. Multiply them. And whatever ratio we are getting in that, in the denominator, okay, see what is the power of individual S. So S is not added to anything. What is the power of individual S? So in this case, power of individual S is 1. That's why this is a type 1 system. How to find the order? You first find G by 1 plus GH. Okay, that's a closed loop system. Find the characteristic equation. In that case, whatever is the power of S, that is called as order. Okay, so where this type is used? Type is used to find out what is the error in the system. We will study that again in the fourth module, I guess. There is the steady state error analysis. There, this type is very much required. So what is the type of this system? There is only a separate S here, S raised to 1. Then the type is equal to 1. If this S was not there, let's say, if it was only denominator S plus 20 and S plus 1000, then what is the type? That means S plus 20 into S plus 1000 only is there at the denominator of GSHS. That means here there is S raised to 1. Okay, so here there is S raised to 1, it's a type 1 system. But if there is only S plus 20 and S plus 1000, okay, so S plus 20, S plus 1000 means there is no S. There is no S means 1 is there, so 1 is given by S raised to 0. So in that case, if there is only S plus 20, S plus 1000 in the denominator for GSHS, we say that this is a type 0 system. In this case, there is only S multiplied, it's a type 1 system. If this was S square, then that would have been a type 2 system. If this was S cube, then that would have been a type 3 system. So we will see what is type and what is its effect in the system. Now we can also write GS equal to Km. So this R and B we are taking outside because we want to represent in a tau form. So tau is nothing but the time constant. So we have seen the time constant in experiment number 3. You have seen for LR system the time constant is given by L by R. In RC system time constant is given by RC. So take this R outside, so this becomes L by R. Okay, so L by R is a time constant. Take this B outside, and this becomes Js by B plus 1. Okay, so J by B is also another time constant. So this is actually the time constant form. So this is Km by Br. So from here I have taken one case R outside, one case B outside. So what we have found is tau L is equal to J by B. Okay, so here it was Js plus B. So take this B outside. So this is that B, and this was Ls plus R. So take this R outside. This R is here. Okay, so now tau L is equal to J by B and tau is equal to L by R. So there are actually two systems. One is the mechanical, whose time constant is given by tau L, and there is another electrical system whose time constant is given by L by R. What is actually a time constant? Time constant decides the fastness or slowness of the system. Okay, so if this values time constant values are very less, that means system will be acting very fast. So this JBLR, they actually decides for system fastness or system slowness. Fastness and slowness in what? Fastness and slowness in producing the output. That means you are giving a control signal, and how fast that control signal is being digested by the system, and controlled output is being generated in how fast. So I'm teaching you very fast, you are grasping, and tomorrow if I'm keeping an exam, you are doing very right. That means your time constant is very slow, very less. That means you are a very fast system. So if tau value they are very small, that means time constant is low. Time constant is very low. If time constant is low, system will produce output very fast. So for fast response, we want lower time constant. So tau L is equal to J by B, some value they have selected for J and B. So this is just a case, they have given 50 millisecond. Tau is equal to L by R, so they have kept it same, and they have produced that L by R is 1 millisecond. So since tau is less than tau L, okay, so tau L is found to be 50 millisecond, tau is found to be 1 millisecond. So as tau L is very greater, we often neglect the tau, because this tau is very less. That means a very fast system it is. So we would have, in that case, this is called model reduction. So this was a third order system. As this tau is very small, that means this part is negligible. So what we are finding is this bigger system, or this third order system, is almost kind of becoming a second order system. So these are tricks which are used in system model. So this is a perfect accurate model, but as this time constant is very small, what we are saying is this is not contributing to the slowness of the system. The slowness of the system is commanded or guided only by the tau L part, because tau L is J by B, which is a very bigger part, because tau L value is quite high. Okay, hence we can remove this. So tau S is very small, that means tau into tau is very small, tau into S is very small, that means only one will prevail here. Okay, so this will become, so the third order system has become now second order system. So whenever there is second order system, that means it will be less complex. So order of the system increases means system becomes more and more complex. Now you can substitute all the values which is given in the previous slide. So here all the values are given. If you substitute that, you'll be finding it to be 0.25 by S into like this, and it will be 5 divided by S into S plus 2. Now you know how to plot this. So now if I'm giving a step input to this system, how you can plot it graph. So whenever I'm saying GS equal to, so transfer function, so this is okay, so this is only GS, I'm sorry, this is only GS. This is not closed loop transfer function. This is only the forward path transfer function. Now from the block reduction, so what we are finding is only for the forward path, that means this part, GS equal to Km by S into this. So the whole thing has been approximated to this part, that is 5 divided by S into S plus 20. So only that plant part, it was a third order system, but second order system. Now multiply Ka with that. Okay, so if you see here Ka into GS. Okay, so it will be overall loop gain will be K into GS divided by 1 plus K into GS, because Hs equal to 1. So that is what now we are finding. So this k into gs divided by 1 plus k into gs. So that's why this is called as batch. And now this is the overall system. Okay, so now this is the reduced model. Okay, there is a little bit of error. There is a little bit of error because that tau s plus one part we are not considering, but it is okay. It will not give a very big error in the output. So there's a k. This is nothing is given. That means it is one. So now you know how to find out what is the overall transfer function. So it is k into 5 divided by s into s plus 20. That is the gs divided by 1 plus k into 5 divided by s into s plus 20. So this is the closed loop system, and if you do that, so it will become like this. So this is the overall closed loop transfer function. Okay, so ys by rs is equal to 5 into ka divided by s square plus 20s plus 5 into ka. Now what is the characteristic equation? S square plus 20s plus 5 into ka is equal to 0. That will be the characteristic equation. And you can change the gain. So if you just keep on changing the gain, you will be finding that this constant is changing. Okay, so this is a quadratic equation. So this is a square plus bs plus c. So c value is changing depending on the value of ka. That means more is the value of ka, you will be finding that the roots will be changing its position. So that is nothing but root locus. As I am changing the forward gain, the position of the roots of the overall system is changing. Okay, so that is actually root locus diagram, and we will see that in module number 4 like this. So ys by rs is this. Now I ask you find step response. How can you find step response? So ys is equal to rs you take right side divided by 5k by s square plus 20 plus s, and if it is unit step input, then rs we substitute as 1 by s. That means ys is equal to 1 by s into this whole thing. Now there will be three roots in the system because rs is 1 by s. Then you have to do partial fraction and you have to find out ys. So there will be three terms here in the right side because rs is 1 by s. So rs I'm taking first right side, and then I'm doing the partial fraction. So there are these two roots are, they may be imaginary root. So even if complex roots are there, we can find partial fraction. So there will be three terms in the right side. So one will be 1 by s, one will be 1 by s plus a plus jb, and another will be 1 by s uh, uh, plus a minus jb. Because if you are finding the roots of this thing, they will be s plus a plus jb and s plus a minus jb, because they will be giving you some complex roots depending on the value of k. And then take rs there, 1 by s, s plus a plus jb, s plus a minus jb. So if you mix them and then take the inverse laplace, you will be finding yt. And if you are plotting that, okay, so if you're plotting that, so this is one another thing you can take in your experiment number 4. Okay, so I will give you the same transfer function and I'll ask you to find out the step response. So this will be one job that you have to do in experiment number 4. I have not yet defined what all work you have to do in experiment number 4. So some 10-15 transfer functions or pole position I will give. You have to find out what is the impulse response and step response. So this will be one of the transfer functions there. And for different value of ka, you have to find out what is going to be the transfer function. So now k is equal to 40, they have assumed. So k is 40 is assumed, then s square plus 20 is plus 200, and rs is equal to zero point 0.1 by s. So they have not given unit step, they have taken 0.1 into ut. Very small amplitude of DC they are giving. Okay, so zero point 0.1 into ut Laplace transform is 0.1 by s. Okay, so that is the input. So 0.1 is the input. You can see here 0.1 is the input, and you are finding that the response disk is almost reaching the same thing. So whatever DC voltage you are giving, so this 0.1 is nothing but the DC voltage. This is the position. This is the expected position, and you are finding that initially it is going little over. The head position is going little over than that. That means wherever it is supposed to reach, उससे थोड़ा आगे जा रहा है वो. But over time it is getting settled to 0.1. So this 0.1 is the command. This 0.1 is a directive given to the disk by us or by the disk driver, that you show a movement which is equivalent to zero point 0.1 unit of voltage. So the disk is moving little ahead because it's a second order system response. We are finding second order system response shows this kind of thing, undulating and you have seen, I think, second order RLC system time domain response. We will do that here also. So we are finding that it is going little ahead, and again it is coming below, beyond, and it is staying here. So this is following the input perfectly, but after a certain time. So almost after, you can see here, this is 0 second, and almost after 0.48 second. So almost at zero point 0.5 seconds. That means after you are giving the input, input is given in terms of some signal to the disk head, almost after zero point 0.5 seconds. So zero point 0.5 second or 0.48 second rather, this point. So from here to here is 0.48 second. So 0.48 second is the settling time. Almost after 0.48 second input is followed by the overall plant. So you are finding there zero point 0.1 unit input is given, output is also zero point 0.1 unit. So this thing you can plot, and I think that's it from my side. So this is what we do actually. First, some system will be given to you like this, and you have to know all the system parameters. Then you have to put them into a model like this, and then you have to assume the values of some of the system parameters. Then you have to find what is the S domain model, and then you have to do some model reduction if possible. So in this case the model reduction is done, and after model reduction you have to define some values, proper values to that. So after model reductions, third order system has become now second order system. Now I will ask you to plot this third order system as well. Whenever you are plotting, plot for this as well, okay, and plot for the reduced system. So you will be finding there will be another graph. There will be another graph here that will be the response for the third order system, and this is the response for the second order system. And then we will find what is the difference between these two graphs. I will show you how to do that. So third order system is the actual system, this is the second order system, and difference between these two is the model error. Why model error? Because there is one dynamics that we have ignored. There is one dynamics. So this is the dynamics tau s plus 1. We have ignored it. We have compensated. We have taken it approximation because tau is very small to tau l. That's why this is not making any big difference. But we can always plot for it in the MATLAB, and we can find out what would have been the exact response if we had kept a tau in the figure. And this is actually approximated response. And difference between these two will be very small, but then also we can find that these two graphs will be different, so that we can find.